In the previous video, we introduced the concept of a quantum circuit, and this was motivated by how we can change the state of a quantum object, like the spin of an electron, by using different operations, mainly applying magnetic fields to either deflect the electron in some given direction or to make it precess or rotate so its spin points in a different direction. Now what I want to do in this video is just go over some of the important concepts of quantum operations. So here we have a very basic quantum circuit, and the first thing I want to highlight is that a very common thing to do is to separate the circuit into two different types of registers. So here in the top, this white line represents what we call a quantum register. This basically represents the region where our qubits live. And then down here below, we have a classical register, which basically stores classical information in the form of bits. So let's first focus on the quantum section of the circuit. Well, first we have just one qubit that we're initializing in state 0, and we discuss some of the ways in which we can take a qubit in an unknown state and reset it to state 0. And then this is followed by operations that happen at different time periods. So a way to interpret a circuit is as operations that happen at some given time. So for example, here at t0, we have our initial state. Then at t1, we apply this X gate. At t2, we apply a Hadamard gate. And at t3, we perform a measurement. Now, quantum circuits are composed of two different types of operations. The first type are what are known as unitary operations. Now, to explain what we mean by unitary, we need to introduce a few more advanced concepts, which we'll cover in future videos. But basically, here the X gate and the Hadamard gate are considered unitary. So unitary operations are reversible operations, but they also need to meet some additional properties that we'll discuss later on. And then the second type of operation that we have is a measurement, which unlike the other two operations is non-unitary or is non-reversible. So what a measurement does is it takes, for example, a state that is in superposition and selects one of the possible states that compose that superposition. And then associated with that measurement, we also get a classical output that we can read in, for example, the form of a classical bit. So let's go over this circuit to get a better understanding of what I mean. So let's start here at time t0, where we simply have our state, let's call it q, equal to 0. Now at t1, we apply this X gate, so an X gate to state 0. And if we represent our X gate in the form of a matrix, on our state in the form of a column vector, we can perform this operation to obtain another vector, which, as we know, corresponds to state 1. So the way we evolve state vectors through unitary or reversible operations is through matrix multiplication. Then at time t2, we apply a Hadamard gate to state 1, and we can do the same thing. We take the matrix for the Hadamard gate and multiply it with the column vector corresponding to state 1. And that is going to give us a vector of the form 1 over root 2, 1 minus 1, which is state minus. Now at time t3, we perform a measurement, and we're not going to describe the mathematical construct for what are known as projective measurements quite yet. All we're going to do at this point is to highlight that if we have this state in superposition, we have that the probability of measuring a 0 is equal to the first component of our column vector squared, or the coefficient that multiplies our state 0. So that will be 1 over root 2 squared. And the probability of measuring a 1 is similarly the second entry of this column vector, or the coefficient that pre-multiplies our state 1, which is minus 1 over root 2 squared. So we know that with probability of a half, at time t3, our state vector is going to go from this superposition state to either state 0 or to state 1. So basically, if we go back to the circuit diagram, we know that here we have state 0, after the X we have state 1, After the Hadamard, we have state minus. And then here on our quantum register, we're going to have either state 0 or state 1, each with 50% probability. Now, if we run this circuit once, or this experiment once, we will certainly get one of these two. But the idea of denoting this way is to show that if we were to run this over and over again, half of the time we'll get state 0 and half of the time we'll get state 1. Now that is for the quantum register, for our qubit, but we as experimenters don't have access to these quantum states. All we can really see are the classical results of an experiment. So in other words, we really can't see the spin of an electron, but if we run it through a Stern-Gerlach device, we can see if it deflects upwards or downwards, and that will be the equivalent of what we will read as a 0 or a 1. So also at time t3, what we will see in our classical register is that with probability of a half, we'll measure a 0, and with probability of a half, we'll measure a 1. So what I want to do now is show how we can simulate circuits like this using Qiskit. And I know we covered some of this in the previous video, but I just want to clarify a few different concepts that we introduced. So for example, we had the quantum circuit class, and this allows us to create circuits with both quantum registers and classical registers and perform measurements. We also use the Statevector class, which allows us to create a Statevector object. So that will be a column vector with some probability amplitudes. But the advantage of using this Statevector class is that it has different methods or functions that will allow us to compute, for example, the ideal probabilities of measuring a given outcome, or we can use the evolve method to apply a unitary to a Statevector and see what the outcome will be. And we also introduced the operator class, which allows us to represent unitaries like the X gate or the Hadamard gate and so on. So I want to show how using these different classes plus a simulator, like the basic simulator that we introduced in the previous video, or the sampler, which we'll discuss today, allows to simulate this type of circuits. So let's first start by importing the three classes we just discussed: the quantum circuit class, the Statevector class, and the operator class. Let's create that same quantum circuit we just analyzed, which had an X gate followed by a Hadamard gate. Let's go ahead and draw it. And the easiest way to simulate what the output of the circuit will be, assuming that the input is initialized at 0, is by actually just taking the Statevector class and passing that quantum circuit object to it. And if we save that in, let's say, a variable q and then display it, we see that we have that superposition state minus, which is 1 over root 2 0 minus 1 over root 2 1. Now we showed this before. This Statevector object has a lot of useful functions, like for example, the probabilities method, which gives us an array with the probability of measuring 0 or measuring 1. Or we can use the sample counts method with some number of shots, let's say 100, to emulate as if we were running this circuit 100 times and performing measurements to give us some set of outcomes. If we do that, we get 50% of the time 0 and 50% of the time 1. Now, we won't always get exactly 50-50. This is just coincidental. If I run it again, we get 51-49, 49-51, and so on. Now, another thing we can do with this quantum circuit object that doesn't have a classical register or a measurement block is to generate the unitary by using the operator class and passing that same quantum circuit. And if we display that, we see we get that unitary that would be equivalent to multiplying an X gate followed by a Hadamard gate. So we can easily see that by, for example, creating a matrix for the X gate using the operator class. And luckily, there's this from label function, which we can use to quickly generate the matrix for the X gate, and similarly for the Hadamard gate. And we can generate that unitary U, not directly from the circuit, but by multiplying these two. Now, the order in which we need to multiply these two matrices is first we have the X gate, which will be acting on a state vector on the right side, followed by the Hadamard gate. So remember that the way we do matrix multiplication, if we have a vector on the right side, the first element acting on that vector will be the one here most to the right, and then followed by the one to the left. This can be sometimes counterintuitive because if we see the circuit, that X gate is to the left, but that's because it's acting on the state vector in the diagram, which is to the left side. So state vector sees that X gate followed by the Hadamard gate, and in matrix multiplication, we'll have the vector on this side. So it first sees the X gate and then the Hadamard gate. So let's call this, for example, U2, and let's display that and compare it to what we got from using the operator class and passing that circuit, which should match. So these are different ways in which we can use the state vector class and the operator class to extract valuable information from a quantum circuit. Now this only works when that quantum circuit only has unitary operations, so no classical registers and no measurements. But if we want to perform a full simulation, similar to what we would do when we execute a circuit in hardware, we need to use a simulator. So let's go ahead and import two simulators, the basic simulator, which we used in the previous video, and also the air simulator, which is from a separate package. It's from the Qiskit air package, but if you follow the installation instructions video, you should have this installed as well. And the air simulator is just a more efficient type of simulator as compared to the basic one, but we want to use both of them just to see the similarities that they have. So the next thing we need to do is to redefine our circuit to also include a classical register and a measurement block. So let's go up here and just copy and paste the same circuit we had, but then let's also add a measurement from qubit 0 to the classical bit 0. And let's make sure that we also specify that we have one classical register. And with this, we can then define our simulator object. So let's call it, for example, sim_basic for the basic simulator. And let's also create one for the air simulator. Let's call it sim_air. And just like we showed in the previous video, the way we execute a simulation was by taking our simulator object and using this run method, passing our quantum circuit and some number of shots. Now, after executing this, we actually extracted our results using this results function. And then from those results, we extracted the counts that represent the number of times we measure either a 0 or a 1 using this getCounts method. So let's actually just label this as counts from the basic simulator. And for the air simulator, we can see that this is pretty much identical. All we need to do is just use our air simulator, but the syntax to execute that simulation is the same. Now here I have a typo. This is actually result, not results. But if we run that again, it should work. So if now we print both of these counts, they should look fairly similar to each other. So we got 52 times a measurement of 0 and 48 times a measurement of 1 for the basic simulator and 50-50 for the air simulator. Now the last thing I want to do is to show how to use the sampler in Qiskit, which is the recommended way to simulate circuits because it matches exactly the way we would package a circuit to send it to run it into a real quantum computer. So for that, we're going to do one more import. We're going to import the sampler v2 or version 2 from the Qiskit IBM runtime, which again is another package that we already installed. And if you want to know the details of why this is version 2, I have a full series of videos on what the sampler and the estimator are. These are known as primitives within the Qiskit ecosystem. And there's a lot of information around this subject, so go check out that playlist if you're interested. But for the purpose of this video, all we want to do is then first define a sampler object. And to do that, we can specify, for example, a sampler using the air simulator, because the sampler is a wrapper around a specific simulator or a specific backend or quantum computer. So what we do is call the sampler v2 class. And here before we used to specify a backend, but this option is getting deprecated. So now we need to use what is known as mode. And here we pass the simulator that we want to use. So let's say that we're going to use the air simulator. And then the way we execute the simulation is very similar to when we do it directly with the simulator itself. We take this sampler object and we do run. But here we can't just pass the quantum circuit like we did above. Here we have to pass actually a list of circuits. But since we only have one, well, we just pass a list with one element, which is our quantum circuit. This is just a syntax change. And the reason for this is because the sampler is designed to efficiently simulate more than just one circuit. So we can pass a list of several circuits that if they're parameterized, we can also specify a list of parameters. And also if we want to use different number of shots for each circuit, we can do that as well. But here we only have one circuit. So we're going to specify the same number of shots. And the way we extract the results from this simulation is the same. We do result. But to get the counts, this is slightly different. So let's first store this in a result variable. And the way this is structured is in the form of a list. And that is because we could have more than just one circuit being executed. So we need to specify for which circuit we want to extract our result. And here, since we only have this one circuit, we need to say, okay, I want the 0th element of this. And then we do data. And then we need to specify the name of the register, the classical register that is storing our results. So if we go up here to our circuit, we see that the name of our classical register is C. So here we have to specify C. And then we do the same as we did for just a straight up simulator. We do get counts. And that's going to give us our counts for the sampler. And if we print that, we see we get a very similar structure to the one we get with the simulator. Now, I know this is a lot of additional stuff we need to do compared to just a simple simulator, but that is because the sampler is the structure that is used to run circuits in real hardware. So we want to know how to do that even with a simulator. So for example, if we were going to run this in a real quantum processor, here in this mode option, instead of passing a simulator, we'll pass the name of the quantum processor we want to use, but everything else will remain the same. Now, one last thing I want to show is how to plot these results a little bit more nicely. So we can do from Qiskit, visualization, import plot histogram. And if we pass that counts variable, it plots a nice bar graph with our results. Okay, now all of this is very preliminary and we'll become more familiar with the different options available with Qiskit as we keep progressing in this video series. We're going to start introducing more advanced concepts and then we'll discover some new features or different features that the simulators have. See you in the next video.